Okay, so basically, as when you metabolize something, it makes it less lipophilic. But a lot of lipophilic compounds are metabolized. Um, so you get, if you make something more lipophilic, it's more likely it's going to be a metabolism substrate. If it's less lipophilic, it's more likely that it's going to get cleared through the kidneys. Now, at a certain point, when it's so water soluble, it's just going to get cleared through the kidneys without there being any metabolism. But basically, what this is saying is that if there's some lipophilicity, then the metabolism enzymes, say the cytochrome P450s or whatever, in the liver, for example, they're going to start acting on your drug. And so this is within um, Lipinski's rules here. And also notice this is the log D. So this is analyzing lipophilicity while taking into account its ionizable groups at pH 7.4, which we said was biological pH. Okay, so this is got a lot of words on it, but it has a lot of different, basically, kind of points and definitions. Okay, so basically, there's going to be two categories of drug metabolism. The phase one is what is how you introduce functional groups, and phase two is going to get more polar derivatives. And so, what we're talking about here is that phase one is kind of putting in different reactive groups, and phase two is making conjugates to biological molecules for excretion. So both of them don't necessarily have to happen to the same molecule. We're going to talk about some molecules that go all the way to phase two, and there are a lot of molecules that do. So basically, there's phase one where they're introducing functional groups, phase two, making conjugates that are very excretable because they become very polar, which means they're very water soluble, which means they're gonna want to be stay in a water solvent, which includes urine. So there's a lot of different things that affect drug metabolism, and it can even in the same person, different days, etc. It's very dependent on many different variables, and so that can be kind of a problem. Another thing to know is that drug metabolism can be both stereoselective and stereospecific. It depends how exacting it is. Sorry. Um, Sometimes the inactive enantiomer produces toxic metabolites, or it may inhibit metabolism of the active isomer. That's just something to know. Um, so there can be a lot of different. All those last 2 points in red and maroon and blue are trying to tell you is that the different enantiomers, what happens to them in the body, can vary a lot. Your body is very aware of different enantiomers of drugs. There's cases, of course, where it's not aware, but it's certainly prudent to be aware to always be making drugs enantiopure because you're not sure if, as you're studying your drugs, what each enantiomer or diastereomers, of course, is going to do. So in the case of ibuprofen, you the biologically active isomer is turned into, or sorry, the biologically inactive isomer is turned into the active isomer. So you don't need to use a single enantiomer. So that can save you some money. So you have to be careful too about seeing what is going to be what happens in the body. So you can administer the rack, which is easier to make, the racemate, and then the body can convert. There's computer software that can be predict it pretty well. So that's pretty good. Um, Okay, I'm gonna kind of skip. I don't really like doing the history stuff, but I should teach it to you. So basically, in the late 40s and early 50s, that's when this came up. Or that's when they started discovering about cytochrome P450. Late 40s and 50s, heme and hemin was really big stuff. That was a big deal scientifically. Remember, this is before they had like the structure of DNA and all that kind of stuff. Okay. So how cytochrome P450 works is pretty neat. So again, we have iron, and we're going in between iron 2, 3, 4, and 5. So it's pretty incredible, all the different oxidation states changes that iron's doing in this process. And so we start here. The iron here is being held in a heme structure. So these nitrogens in the square are denoting the heme that's holding the iron 3. And what's going to happen is that we have a reducing agent and an oxidizing agent that's eventually going to have the activated coenzyme, which is going to be this iron attached to what's an electrophilic oxygen. So this can do radical chemistry, or well, it basically does radical chemistry. We'll say it will do stuff that it looks like 2 electron. So there's a number of different reactions that happen here, but they all kind of have the same flavor, which are these oxidations, right? So you can oxidize an aromatic group to a phenol, for example. You can oxidize a double bond. And so these are a number of different, you can oxidize at the halogen, or alpha to the halogen, sorry, or at the nitrogen or chalcogen. We talked before about drug-drug interactions. Here's another example of that. So you can see that this is the active ingredient in St. John's wort, which is a natural antidepressant. And you can imagine that this is going to be a good substrate. If we look at these previous double bond setups, this is going to be a good substrate for cytochrome P450 here. So lipophilicity and ionizable groups are important for how things are going to bind to cytochrome P450s. And the thing is going to be determined by a number of things, like electron transfer from the compound is going to be important. Ease of H atom extraction, that's, for example, alpha to a carbonyl, right? Remember the pKa is kind of low there. It's around 16 or 17, depends. It can vary widely, of course, by a factor of about 10,000 to 100,000, but basically it tends to be pretty acidic there. How the active site of the enzyme is able to what it's able to accommodate, and etc. So there's another oxidant that we're going to start talking about too, and that's flavin monooxygenase. So that's another oxidase. So we have cytochrome P450 oxidase, and we have flavin monooxygenase, and so that's another important oxidizing enzyme. So we're going to go over the mechanism of that.